I'm going to get started. My name is Iqbal Khan. I'm a technology evangelist at Alachisoft. We have a product called NCache, which is a distributed cache for .NET. This talk is not about NCache. It's about overall issue of how to scale .NET applications with distributed caching. So I would prefer to keep this a more interactive discussion. So if you guys have any questions as I'm talking, please raise your hand, and we can go over that question right at that time instead of waiting until the end. Okay. So, actually, you know what? I forgot to do one thing. Sorry about that. I always do this. I need to record this session for our purposes. I'm going to repeat a few things. Sorry. So, my name is Iqbal Khan. I'm a technology evangelist at Alachisoft. Thank you for coming to this talk of how to scale .NET application with distributed caching and this live 360 event in Orlando. So let's start with some definitions. I'm sure most of you know this already, but we'll just go over it for completeness purposes. The first definition is scalability. So what is scalability? People often confuse scalability with performance. Performance is really fast response time by your application, but that could be with 5 users only. And if you take that from 5 users to 5,000 or 50,000 users and that performance remains good, then your application is scalable. That's the nutshell of what we're trying to achieve. In whatever application you have, if you can achieve the same performance that you had with 5 users or really low transaction load, if you can achieve the same performance with high transaction load, then you are scalable. If you don't have good performance with 5 users, then you have other issues. Linear scalability is more of an infrastructure definition, which is that if your application is architected in such a way that adding more servers to the deployment, whether that's adding more application servers or database servers or whatever, if that can increase the transaction capacity in a linear fashion, then you have a linearly scalable application architecture. However, if you are not able to do that, if adding more servers is not adding any value, then there's something fundamentally wrong, and you're not able to scale the application in a linear fashion. The goal here is, of course, to be able to scale in a linear fashion. Non-linear would be where as you add more servers, you see increase, but at a certain point after that, there's no more increase. In fact, there's a drop of performance even if you're adding more servers, because the architecture of the application and the deployment, there's some bottlenecks which you're just not able to overcome. Which applications need scalability? These are usually web applications, so these are ASP.NET for .NET folks. Web services, backend for the Internet of Things, which is a very strong emerging space, and big data processing. Big data processing is more common on the Java side. Not a lot of people do it in the .NET side, but big data processing is also another space. And any other server application. This could be your batch processing application. You may be a financial services company and you have millions of customers and they call and change addresses, or maybe they're transferring funds from one account to the other, and you have certain compliance requirement that by the middle of the night or something you have to complete those processing, and there's some batch processing happening in the back end in a workflow manner. So any other server applications that are under time constraint to get a certain number of transactions done need scalability. So where is the scalability problem? We talked about linear and nonlinear scalability. So the scalability problem is that the application tier scales in a very nice linear fashion. If you have a web application or web services, your application tier, you just add more servers, no problem. It's the data storage that's the bottleneck. And when I say the word data storage, I mean relational databases and mainframe legacy data. I don't mean NoSQL database. NoSQL databases are great. We also have a NoSQL product called NosDB. But NoSQL databases are not always the answer. They are an answer if you can move. The more data you move to NoSQL databases, the more of a scalability solution you get. But the problem is that you cannot move all data to NoSQL. There's a lot of data that has to stay on relational for both technical and business reasons. So relational databases are here to stay. They're not going anywhere in terms of this problem. So you have to work around this reality or work with this reality that you are going to be working with relational databases. And still you have to solve this problem. And the reason you have to solve this problem is because you have all those applications that I mentioned that need scalability. And the answer, of course, is to have a distributed cache plugged in between the application tier and the database tier. So a distributed cache is essentially, it's a very powerful and yet very simple concept. You have two or more low-cost servers, and they're clustered together, and they pool that cluster pools the memory and the CPU resources of all the servers together into one logical capacity. The bottleneck in scalability comes in three areas. One is memory, second is CPU, third is network card. So if you have, let's say, one database server here, and you have 20 application tier boxes, that one database server, you can take it up in terms of the hardware strength is concerned. You can add more memory, a lot more CPUs, but there's a limit to that. So the answer is to be able to have more and more servers which are not very high-end. In fact, they should not be high-end. By definition, what we've seen over the last 10 years or more of doing this is the most common configuration is a dual CPU quad-core type of an equivalent. So let's say an 8-core box. And a 16-core box is actually a pretty high-end configuration for a caching server. 8 cores is pretty much the common. Memory, of course, you need a lot of memory because, and memory is cheap, so it's not a big factor. You need a lot of memory. Why? Because a distributed cache is an in-memory store. So it stores everything in memory, and a typical configuration would be about 16 to 32 gig of memory in each cache server, and 2 cache servers is the minimum you should have for redundancy purposes. And so by having this architecture, now you are in a situation where as you add more servers in the application tier, you add more servers proportionally in the caching tier. So usually it's a 4-to-1 or 5-to-1 ratio is what we've seen as the most practical one. In some cases you can go a lot more than 5-to-1. Means 5 application servers to 1 caching server. But there's no limit to how many servers you can have. You can have 2, you can have 4, 10, 20, 30 servers. But for you to have 20 servers here, you probably need 100 server in the load balanced environment. So at some stage, that becomes pretty much a high end of any application that we've seen in the web or e-commerce on online business scenario. So by adding more servers here, this is no longer the bottleneck. So the distributed caching is actually becoming a best practice if you have scalability as a need. Because now not only do you have a database, which is there for its own purpose, you need permanent data store persistence for all the application data, but you also have this really, really fast and scalable infrastructure, which is part of your application architecture now. So when you're programming, you're no longer just programming for the database. You're always thinking of a cache, because the cache will now make sure that your application never slows down, even under peak loads, even though the database wasn't designed to scale in the same fashion. This is a typical picture. About 80% of the traffic will get trapped, or will be 80% of the time you will go to the cache, 20% of the time you will go to the database. And that those 20% are mostly updates. And of course some reads, because you need to get data into the cache. But you can also pre-populate the cache, and there are a lot of other ways to do that. But by reducing traffic so dramatically, in the database tier, that's how you achieve performance and scalability. Any questions on this so far? So that's kind of the case for using a distributed cache, why you must keep that as part of your application architecture.
So are these cache machines physical machines, not virtual?
They could be virtual. In fact, most of them are virtual these days, but they could be physical. These are just, and any distributed cache, like NCache would be, and also Redis, I mean, this is a software. So you install it on the operating system of your choice, and that's how it runs. Most of our customers use NCache on VMs because that's pretty much the standard way of doing anything these days. There's a slight performance drop between a physical and a VM, but it's not noticeable. You can add more boxes to compensate for that very easily. Any other question?
Is that 20% mostly the write stuff?
Most of these are writes and some reads because you need to populate the cache. And you can even reduce the reads by pre-populating the cache, depending on what features the cache solution that you have is offering. For example, NCache offers you a cache loading feature so that you can automatically pre-populate the cache based on whatever you think is the expected data. And that's not all the data. Of course, the application logic still needs to be where if it's not in the cache, go and get it from the database type of thing.
How do you control the refreshing cache from the...
Okay, I'll actually come to that, but the so the main thing that I want you to understand up until now is that your scalability problems will go away if you use a distributed cache. And what a distributed cache looks like in your deployment environment. So now that we've kind of made the case for using a distributed cache, the next question is, well, how do you use it? Where do you use it? What type of usage should you have of a distributed cache? Well, the most common use is the application data caching. This is where, as I was just talking about, whatever data you have in the database, you cache it so that you don't have to go to the database. The thing to keep in mind, and I'll go over this point in more detail in the follow-up slides, is that in an application data caching use case, the data exists in two places. One is in the database, which is where it always has to be, and second is the cache. So whenever data exists in two places, what's the first problem that comes to mind? Syncing, yeah. So any cache that cannot handle that situation forces you to cache read-only data, data that you know is never going to change. In fact, most people, when you talk about cache, the knee-jerk thinking that comes to their mind is, well, it's for read-only data. I really don't want to cache my customers and accounts and data that's changing every 30 seconds. But the research shows that the biggest use of a cache is in the transactional data, and once you cache it, you'll probably need it in the next 1 minute or 2 minutes. Whatever that activity, whatever that moving window of your use is, that's when you'll need the same data again. And if you can get it from the cache, you're reducing those trips to the database. And multiply that by millions of transactions that are happening in your application, and it becomes a pretty significant boost. So keep that issue in mind as we go forward, that any good cache must handle that very, very effectively. Second use case is if you have an ASP.NET application, there's a lot of transient data. Transient means temporary, and that you can put in the cache. And this data doesn't really belong in the database. For example, a database is there for permanent. It's a permanent store. It's that's your master record. So a session state, you probably need to keep it for only as long as the user is logged in, maybe 20 minutes after. So why keep it in the database? Database is not as fast. Relational databases were not designed to store blobs, and sessions are usually stored as blobs. So there's a big performance hit when you store sessions in the database. So session state is a very good use case for ASP.NET to put it in the distributed cache. And if you are not using the MVC framework, then view state is also there, which is a pretty heavy piece of data that flows from the web server to the browser for only one purpose, to come back to the browser on a postback. So it's a pretty long trip, for nothing, as they say. So it would be so much nicer if you could just keep it on the server side and just send a small key. So that's a very, very good use case for caching. The third use case is page output. A lot of your pages, their output doesn't change every time. So if it's not changing, why execute the page? Because when you execute the page, you're consuming the CPU and the memory and all other resources. Why not just take the output from the last execution and display it? So Microsoft or ASP.NET has an output cache framework where you can plug in a distributed cache. So now in this use case, in these three use cases under ASP.NET, the nature of the problem has completely changed. It's no longer synchronization between the cache and the database. Why? Because there is no database. Cache is the database. The nature of the problem now is, so cache is in memory, right? That's how you get all the performance. So when you're keeping data in memory and that's the only store, what is the biggest concern that you have? You might lose it. What if that box reboots? Windows is known to reboot or recycle worker processes. So what if, even if a Linux box would have to reboot, but what if your box reboots? Are you ready to lose that data? What if you're an airline and that customer was in that last page of hitting submit of $5,000 worth of that family vacation ticket that they were going to buy for Hawaii, and suddenly it says, sorry, you got to start all over again. And they went through all sorts of flight research and check times and did Google flights also and see which ones matched and all that other stuff. So, not a good experience. As a business, you don't want to lose customer, the shopping cart, you don't want to lose that. So, the answer to that is a distributed cache, you should only keep sessions in it or all that transient data if it can ensure reliability, if it ensure that you'll never lose that data. How does it ensure? It does replication. So a good distributed cache does replication of data across multiple servers. Now, replication is actually a waste of time. It's extra thing that we're doing just for that contingency that we're just talking about. So the negative side of replication is that it has a performance hit. So if a cache doesn't do it intelligently, and a lot of them don't, then you'll see a performance hit when you turn on the replication. So keep these 2 points in mind. And the third use case is what most people don't know, actually, that a distributed cache, once you have that infrastructure in your environment, it's a very powerful event-driven data sharing platform. So you may have multiple applications that need to share data in a workflow. You may have a pub-sub type of a situation, that you are going to probably use a message bus, enterprise service bus, or a message queue for it. A distributed cache is a very powerful platform for that. Since you have it in-house already, it's actually faster and more scalable than the other options because it was designed for performance, whereas the other applications were designed more for sharing only. So event-driven pub-sub type of a sharing between multiple applications. So one application produces some data, puts it in the cache, fires off an event. There are other applications which have registered interest in that event, that I want to consume this data whenever that's available for me. So they receive the event, and again, one application could be here, one application could be here. This becomes this very, very, very powerful, scalable event engine that they can all tap into. So that's a third use case. Even in the event, in the runtime data sharing feature or use case, most of the data is transient, although it's being derived from permanent data, and it could probably be recreated from that permanent data, but it's a lot of work to do that. And that data is usually in this temporary, because the nature of that use is temporary, it's not usually, it doesn't need to be saved in the database. It just needs to be consumed. So cache is, again, the only store that it'll be in. So just like the sessions and others, the issues are the same, that reliability has to kick in. So those are the three common ways that you would use a distributed cache. Any questions on this? Okay. Oh. actually, I was gonna. So let's get this out of the way first, because I used to have this slide afterwards, but then I changed it in my last talk and I forgot. So the nice thing about these three use cases is there's no programming needed to do that, because the ASP.NET framework allows you to plug in a third-party provider. So for sessions, for example, if you were to have, I'm just going to quickly show you one quick sample where all you do is you go to the web.config, and of course in the ASP.NET Core that paradigm is going to slightly change, but the idea is the same. So if you go to the web.config, this is just a simple ASP.NET application. You go to web.config, you need to first of all add the assembly of whichever cache you're going to use. In case of NCache, you're going to just do the add assembly on the NCache session store provider, and you can just copy paste. And the second thing, which is what you need to do really, is to make changes here. So there's a session state tag in the web.config where you need to make sure that the mode is custom and the timeout is whatever your timeout is going to be. And in case of NCache, then you need to actually just add this line. And there are a bunch of other parameters that you need to specify, that you can specify, that I'm not going to go into, but one of them is to just the name of the cache. In case of NCache, all caches are named, and I'll actually give you a demo of that too. But so you just specify the name of the cache. The cache is already created. That's like a connection string. That tells you which cache to connect to, because you might have multiple caches, one for sessions, one for application data. So, and that's all. I mean, you make that change, and you just do a sanity test, go through all the common use cases of your application, and your application is suddenly ready to store sessions in a distributed cache like NCache. So the easiest way to benefit, and the biggest gain actually, is sessions.
What happens when the cache gets full, when you have cache-only data you're talking about hanging around?
Yeah, a good quick question. So in case of session or in case of any transient data, if the cache is the master store, one issue was replication. The other is definitely the cache could be full. Because you've only a good distributed cache would allow you to specify how much memory you're supposed to use, because there may be other processes on that box, or even if there aren't other processes, memory is limited. So you specify like a maximum size of the cache. And once the cache reaches that size, there are two things that it can do. One, it can reject any further additions, which is probably not very desirable. And second, it can remove, or what we call evict. It can forcibly remove some of the older items. So there are different algorithms that different caches provide. NCache gives you three different algorithms. There's the LRU, the least recently used algorithm, the least frequently used, and the priority FIFO. So based on the algorithm of your choice, you can say, well, evict 5% of the cache, or 10% of the cache. So it's going to go through and evict that many objects. Having said that, you really don't want to do any eviction. So what you want to do is do your capacity planning, where there's a term called eviction, which is forcible removal, even though the item hasn't outlived its life. It's still considered active. Or second is called expiration. Expiration is pretty much something that almost all caches provide, especially the absolute expiration. And you can use the absolute expiration to implement the sliding expiration, or the other way around, I think. So sliding expiration, and I was going to go into that later, but expirations are a way for the item to themselves be removed without even reaching this case where you don't have any memory left. Because again, you don't want to evict an active session just because that user went for a cup of coffee and he came back and he's still within his 20-minute limit of session expiration, whatever the session expiration you specified, that just because the cache was full, his session's kicked out. That's also not a good use case. So you want to do the capacity planning. And with NCache, at least, there are a bunch of tools that we have that let you quickly analyze what the memory footprint of your application objects are. And based on that, so you put this NCache into your infrastructure. You do what I just showed you. You run your application average use cases, and on a monitoring side, NCache will show you what the average object size was and how much memory it consumed and stuff. And then based on that, you can extrapolate what are your peak loads going to be and how much memory you should have. And as I said, a typical cache server is 16 to 32 gig memory. It can be more than 32, but that's typical. So you can add more boxes. So that's how you do your capacity planning. Good question. So that's all you have to do for the session state usage in a distributed cache like NCache or any other. And the same goes for view state and output cache. It's all a configuration-based change. So I'm not going to go into those, each of them. I just wanted to show you this as an example. So let's come to the heart of a distributed cache. And I say heart because that's where most of your time is going to be spent. If you choose to incorporate a distributed cache, you will be doing most of your time doing application data caching. So what does a typical API look like? If you guys know ASP.NET Cache object, NCache tries to mimic it as close as possible, although we are a superset, so there's more. Every cache has its own API. This is what an NCache API looks like. You connect with the cache. It's a named cache. You get a cache handle. You keep that cache handle around, and within the application, you just do cache.get, get, contains, add, insert, remove. There's also an add async, insert async. Insert means add if it doesn't exist, or update if it already exists. That's the same terminology that ASP.NET Cache object uses. That's why we also used it. And the async method basically means that you don't have to wait for that operation to be completed. You can actually, there's a third parameter, which is that you can specify a callback. So your callback will be called in case something goes wrong, or else you can pretty much assume that everything went fine. So let's quickly see now. So when we were here, we talked about application data caching. The biggest concern is that you have to keep the cache fresh. So a good distributed cache must allow you to do that, because if it doesn't, it forces you to cache read-only data. Read-only data is about 10 to 15% of your data anyway. So how are you going to really get benefit out of this cache if you're only caching 10 to 15% of what you should be caching? So what you want to do is cache all data, practically all data. Very, very few pieces of data would be where you say, it really doesn't make any sense to cache. But almost all data, some of the data you'll cache for a short time. So, but once you cache that data, this is all application data. How does the cache ensure that the cache stays fresh? There are different ways that it can do that. Number one is expirations. Expiration is, so there's an absolute expiration, there's a sliding expiration. The two have very different meanings, even though they both are expirations. Absolute expiration is what you should be doing for keeping the cache fresh, because you're making a guess. You're saying, I'm saving this customer object in the cache. I think it's safe to cache it 5 minutes. You're just making a guess based on, it's an educated guess, but it's a guess. Within 5 minutes, you hope that nobody's going to modify it in the database. But if they do, then your cache will be inconsistent with the database. Sliding expiration, on the other hand, has nothing to do with keeping cache synchronized. It has to do with the eviction, it has to do with the automatic cleanup of the cache. So sessions, you're saying when there's nobody logged in, after 20 minutes of inactivity, remove the session. So you're doing like a cleanup. You're saying the cache, please clean it up for me. I don't want to have to keep track of all of this. I've put it in the cache. I've specified how long it should stay in the cache, even if nobody's touching it. After that, clean it up. So very different goals that you have from from absolute expiration versus sliding expiration. So sliding expiration you would use for sessions for transient data. Absolute expiration you would use for permanent data. Another term I want to use is reference data versus transactional data. Reference data is data that does not change very frequently, but it does change. It's not a read-only. It's your product table, which the price might change every day or every week or something. but it's not as frequent as a customer object or an activity object or something, or an order object. So transactional data is what we want to cache. Of course, reference data is a given. We want to cache that. But transactional data is also something that's where we're going to get all the data. So if expiration is not sufficient to ensure that your cache is going to stay fresh, then you need to have more features. So the next feature, a very powerful feature that a good distributed cache should have, is that it should be able to synchronize the cache with the database without involving you, without having you monitor things. So you should be able to tell the cache, I'm caching this object. This is related to this data set in the database. So please monitor this data set in the database. If it changes, please go and do one or two things. Either remove this item from the cache. Removal means that next time the application wants it, it will not find it in the cache. What happens when you don't find it in the cache? You get it from the database. So, that's like getting a new copy. Or second, it might just reload a new copy automatically. Reloading a new copy automatically requires another feature called read-thru, which I'll talk about. So I'll come back to that. But database synchronization is a very, very powerful feature. This is what gives you peace of mind to make sure that your cache will stay fresh, that you will not have to worry about whatever data you're caching. And there are different ways to synchronize the cache with the database. The most common is SQL dependency, which is actually an ADO.NET or SQL Server feature that NCache uses. So for example, I didn't show you the code. I was supposed to. So I'm going to quickly show you what the code looks like. Where'd that go? So if you have a .NET application, let's say this is an NCache, of course, you would reference two of NCache libraries, NCache.runtime and NCache.web. So as again, we've tried to name it as close to the ASP.NET cache object namespace. So NCache.web. When we came out back in 2005, ASP.NET cache object was the only cache around. So we were the oldest. We're the oldest in the space. So that's why we picked that name, to make it easier for people. So within the application, you would include a couple of NCache namespaces. Then you would connect with your cache. You get a cache handle. And now you have a cache handle. So let's say you create your object, and you want to do cache.add. So cache.add takes a key. Notice the key is actually it's a string. So we've followed this is not following that naming convention, but usually it's customer : customer ID : whatever the ID was for that customer. So you do cache.add after, and then in this case, it is specifying a 1 minute absolute expiration, and saying don't do any sliding expiration and all the other stuff. So it's just to sort of give you a flavor of what a cache looks like. Very easy to use, very simple API, much simpler than doing ADO.NET or any other programming.
So this is like an in-memory cache then. So I mean, would you have like a caching service that everybody call? I mean, how does it get the distributed part against like a web farm or something like that?
Okay, let me just this is good. Let me actually show you what a cache looks like. What an actual cache. So I have these VMs in Azure. So I've got demo 1, 2. These are two cache servers that I'm going to use. These are cache VMs. And I will have my application server. I'm just going to call it demo client. So my application is going to run on demo client. Okay. So I have remote desktop into this. I'm going to, in case of NCache, I'm going to run this tool called NCache Manager. I actually have it here. And I will go ahead and create. Let me just quickly make sure there's no cache already by that name. There's none. Okay. So I'm going to go ahead and create a new cache. I will call my cache demo cache. I'm going to just take everything else as the default. I will pick a caching topology. I'm not going to go into the detail, but this caching topology does both partitioning and replication at the same time. So when you do this topology, your cache will look something like this. So these are your cache servers. So some of the data, this 1, 2, 3, 4 are the data elements. So some of the data is in partition 1, some of the data is in partition 2, and every partition is backed up onto a different server. So if you had 3 servers here, let's say you would have partition 1, 2, and 3. Server 2 has the replica for partition 1, server 3 has a replica for partition 2, and server 1 has replica for partition 3. So this is what, so the cache actually is a server. It's actually more than one server, which is in a cluster. They know each other. And I'm going to quickly now take you back to this. So let's say I've picked a partition replica topology. Come on. Okay. I will pick demo 1 as my first cache server. Why is it so slow? Demo 2 as my second cache server. I think it's probably because the internet is slow, maybe. I don't know. So I've got a 2-node cache cluster. So demo 1 and 2 now know about each other. So they're going to talk to each other on this port, on port 7802, which I could change. Why is it so slow? Just want to make sure. Oh, there's no CPU here. Okay, so the next I'm going to specify how much memory the cache should have. So it has 1 gig. You'll probably have, as I said, 13 gig or something. And then I'm going to specify the eviction policy, which is least recently used. I'll say 15%. I'm sorry, evict 5% of the cache. This is really slow. I don't know what's happening. This whole box is slow. Even a click is, even though the CPU is not. Yeah, looks like it. Yeah, it is. Okay, I'm gonna. So basically, you have a cluster of servers that logically are called a cache, and you know them by a demo cache only. On your box, let's say your application server box. Let's say here's NCache is installed here. You're going to have a config file, which will have that cache name and a list of servers that represent it. So that's just a starting point. But again, you will know that entire cluster as just a cache name, and you connect to it, and then your client API will connect to all the cache servers in this picture. In case of partition replica, every client talks to all the servers, so it can go directly where the data is, the partitioning part. One cache is on multiple servers, and on the same servers you can have multiple caches.
Okay, so you can have a logical separation or
actually, on the same 2 boxes, I've just created a demo cache which was on 2 boxes. I could create another cache called demo 2, which will be also on the same 2 boxes, and it will be a separate isolated cache. So on the same set of VMs, you could create multiple caches, and every cache usually will span more than one server. So let me. So the expiration. So that's what this was doing. Okay, I'm just going to quickly, now that it's back up, so I can complete that part of the presentation. I'm going to go ahead and add a client for this, which is my demo client. I'm going to go ahead and click on the cache. This is still taking a long time to click. And I'll say start the cache. So just by saying that, the cache will start on both of those boxes. NCache is a Windows-based cache, so it has all the easy to use capabilities that a good Windows-based product has. So you can do all of this from a central place. All this you can also do through scripting. So I'm going to just watch some perfmon counters. Come on. Yeah, this is really slow. Actually, I'm just going to go back. Okay. So,
If your application is getting something from the cache and you're planning on doing an update on it, you want to surround it in some sort of transaction so that somebody else coming in on one of the other servers, do you have something, I don't see in the code, something to protect that?
actually, the distributed caches, none of them provide transaction rollback capability. NCache has partial transaction support through locking. But the rollback is something that is not provided because it's distributed. It's a performance issue. So what we recommend is if you have a multi-item transaction in the database, commit the transaction first and then cache it. So it's only once you've committed it successfully, now you know the database has accepted your updates, then go ahead and cache the stuff. The cache itself will never need to reject any data. The only time it rejects any data is when it runs out of resources, or when there's a network issue or something. So there's no rejection of data like a check constraint has been violated or referential integrity has been violated, which is what a database, a relational database would do. So a rejection of data in a relational database is a normal thing. That's part of your normal operation that you need to cater for. In caching, that's not a normal thing. You should not be having failure of data entry, because it doesn't care what the data is. It's a key and an object, object being the value.
So you say, I don't think you quite, I don't think we're talking the same. Let me see if I can rephrase this with an example. Let's suppose that I want to keep a count in my cache of the number of active sessions that I have. 1,000 users coming in during this hour or whatever. It's not something I want to keep in my database. It's something I want to keep in my cache. And so when somebody new comes in, I want to get the current value, I want to bump it by one, and I want to store it back, but I want to make sure that that's atomic. Semaphore lock or something.
That much you can do. At least with NCache, you can do that. There's a locking feature. So there are two types of locking that NCache has. One is called optimistic locking, which is it's a versioning thing. So multiple clients can read the same thing, but only the first one gets to update it. The second one, when they update, they'll be rejected, saying, well, I have a newer version than you do. So that's one. The second is you just lock. You just say lock. And there's a get and lock and an update and unlock method. So once you've locked it, then nobody can read or write that item until you've unlocked it or the lock expires. At least NCache has that feature. I don't think anybody else has that feature as far as I know. I don't think Redis has that feature also.
So when you say commit the transaction and then update the cache, so your app has it connections in directly to the database which you use for writings and then use the cache for reads.
So basically, when you're updating the cache, you first update the database because you want to first make sure that
As well as
exactly. So your application has to talk to the database. It needs to first commit the transaction. Once the transaction has been committed successfully, then it should go and put the data in the cache. If you don't have a multi-item atomic transaction, if the only thing that you're updating is one, then that update itself is commit, right? So at the end of that, you can go and update the cache. But it's only if you need to update multiple items as one transaction. Any other questions? Okay. So let me show you what database synchronization looks like. So for example, what you do is, again, it's the same type of an application. You've got the cache. And when you try to add a data to the cache, let's say you're doing cache.add here, and this is, of course, NCache code, you specify a SQL cache dependency, which is an NCache class, but it maps on the back end to the SQL Server SQL dependency class. And you pass it a SQL string, which is then used by NCache to connect to the database, and the cache server now becomes a client of your database. So for example, if your application is here, let's say your code is running here, you just issued this call, oops, sorry. You just issued this call of cache.add, and you pass this SQL cache dependency. The client sends all of this to the cache server, so one of the cache server or multiple, and the cache server now opens a connection to the database because you've specified a connection string also here. And this connection string is, of course, pooled. So if multiple times you specify the same connection string, then there's a connection pool on the back end. So now the cache now has become a client of your database. It will monitor your database, and so the database will notify the NCache server that this data has changed that you've asked me to monitor. And the NCache server at that time can decide whether it should remove that item from the cache or reload it from the database. And to reload it, you have to actually go through the read-through feature.
Is there any settings that you have to have at the database or configuration you have to do for that to work?
Yes. So SQL dependency is a feature of SQL Server. To use it, you have to configure SQL Server. There's some information that you can get on our website on how to do that. You just have to turn on the SQL broker and stuff like that.
The reason I was asking is a lot of the queries and the way our tables are set up, you can't use views to get that
Right.
dependency to come back. I was wondering if you had something that handled that.
No, actually, this is purely a SQL Server feature that we are leveraging to be able to give you the synchronization. So that's one way to synchronize the cache. There are also other ways. Any questions on the SQL dependency, how it synchronizes the cache with the database?
Does that use a query notifications from the database?
It does use the database notification, yes. So SQL Server sends a notification through its client API because NCache is now a client of SQL. And the same thing happens with Oracle also, So there's an Oracle dependency, there's a SQL dependency. So both of those work. Okay. So that's one way to do it. It's really powerful. It's event-driven. As soon as the change happens, the database notifies the cache immediately takes the action. However, there's an overhead on the database server end, because every time you do a SQL cache dependency, a data structure has to be created within SQL Server to monitor that data set. Now, if you had 1 million of these, I can guarantee you your SQL Server is going to crash. So again, since we're talking scalability, you need to think in terms of really large numbers. So if you have thousands or tens of thousands of these, no problem. But if you have hundreds of thousands or millions of them, then a different strategy would be a better strategy. One other strategy is called DB dependency, which is our own NCache feature, which is a polling-based dependency. We've implemented this where there's a special table, and we ask you to modify triggers so that you can update the flag in that table for that corresponding row. And then whenever you do a DB dependency from the cache creates an entry in that table, and then in one fetch, the cache can fetch thousands of rows where the flag is true. The update has been happened. So it's like our own way of keeping track. It's polling based, so it's not instantaneous. By default, it's about 15-second delay, but you can reconfigure that. You don't want to poll too frequently either. So that's the other. But even there, you have limitation of what if you have 1 million rows in that table with the flag of true and false, the index would look pretty big, right? There's a true and there's a false index. Those are the two nodes of a tree, So there also, so DB dependency is more efficient than SQL dependency, but not as real time. But even it has limitations. The third one is the CLR procedures, where you can actually call a CLR procedure from a trigger in the database. So whenever any item is added, updated, or deleted, you call a procedure. The procedure makes an async call to the cache. It says, please add or update or delete this item from the cache. The reason async is critical is because you don't want to delay the transaction, the database transaction. It's going to start timing out otherwise. So an async call will immediately return, and at least the database transaction can commit, and the cache can be updated. So the synchronization of the cache with database is critical feature. You must have that. And the same thing if you have non-relational. You may have mainframe or legacy or any other data source. You may have a cloud data source. You may want to make a web method call to even check whether that data is updated or not. And NCache allows you to have this custom dependency feature where it's your code that can monitor. NCache calls your code every small interval. You go and monitor your data source to see if that data has changed. If it has, you notify NCache, and NCache will either remove or reload, again the same way. So keeping cache fresh is critical. Any cache that doesn't let you do that, it limits your ability to benefit. I'm going to skip the handling of relational data, although even that is not. Well, let me quickly say it. You have one-to-many relationships, one-to-one relationships. So if you have one item in the cache and many items also in the cache, when you remove the one item in the cache, logically the many items should also be removed. Because what if you've deleted that from the database? So the cache should be able to keep track of all of this. You could do that in your application, but it just complicates your application quite a bit. Because now you're doing a lot of bookkeeping for the cache. It's like you're building in database synchronization or data integrity code within the application, which is not the job of your application. You don't do that for the database. The database does it for you. So the cache should also do it for you. Any questions? Okay. So read-through, write-through is another very powerful feature that your cache should have. Read-through is basically, again, the concept is very simple. You implement an interface. In case of NCache, you implement an interface called the Read-through provider. Where did that go? Right here. Can you see that? Yeah. And it has three methods. There is an init, which gets called when the cache starts, so that you can connect to your data source. There's a dispose when the cache stops, you can do your cleanup. And most of the time, you are called this load from source. So it passes you a key. The key is your key to know, which item in your data source to fetch. And then you give it back, in case of NCache, a provider cache item. And you can specify expirations and resync on expiration, all sorts of flags here, and then pass it on to NCache. NCache then caches it. So how does read-through work? The way read-through works is your application always asks the cache. It says cache.get. If the cache doesn't have the data, instead of saying I don't have it, it goes and gets it from the database. So your application suddenly becomes much simpler. It no longer, a lot of the persistence code you've just taken out of your application. Because, so one benefit of read-through is that you've sort of simplified the code, you've encapsulated it all into the caching tier. The caching tier now has more and more of your persistence layer. Not all code can be done through read-through, but a lot of it can be. The second benefit of read-through is what I talked about earlier, which is the reload feature. Now, imagine if you have an e-commerce application and your pricing change, so every time pricing change, those items have to be removed from the cache and reloaded. But it's really heavy traffic. So while they're removed, a lot of client requests will hit the database. The first one will fetch it and put it in the cache. But until that time, the cache suddenly have a lot of unnecessary traffic. And if that keeps happening, if you have a lot of that happening, the database is going to get a lot of unnecessary hits, which you could have avoided if you had just said reload on expiration. So reload on expiration, what does that do? It does not remove the item on expiration. It just reloads it. So when expiration happens, the cache will call the read-through and go and get it from your data source and just update. So there's only an update operation happening. There's no remove and add operation. And because of that, the data or the item is always in the cache. So the cache suddenly now becomes, it can take care of itself. It can go and reload itself whenever data needs to be reloaded. So that's a really powerful capability of read-through. So when you combine that with expiration, and you can do that also with database synchronization. When the database synchronization happens, again, why remove it? Just reload. The other feature is write-through, which works just like a read-through, except it does writing. There's one more thing that it does. It can also do bulk write. And the reason it does bulk write, I'll explain in a bit. So the same way, there's an init, there's a dispose, and now there's a write to data source. The write does not mean add or insert only. It also could be delete. So the write has an operation type, which can then either be add, insert, add, update, or remove. And that depends on what the cache operation was. And then you can also do that on a bulk. So the write-through has the same benefits of read-through in terms of simplifying your code, but again has one more benefit. So read-through had the reload benefit. The write-through has the benefit where you can write behind. And write behind is a very, very powerful feature. Why? Because the database updates are a bottleneck. Again, database is that necessary evil that you have to live with. You cannot live without it, but it's causing all sorts of bottlenecks in your application. So the less you can depend on it, the better your application. The fact that you cannot live without it, you still have to have it. So what does a write behind do? It says you update the cache, which is super fast, 10 times at least faster than the database, if not more. And then the cache takes care of the database update. So there's an asynchronous write-through. That's the write behind. So you will go and update the cache, come back, and you continue your stuff, and the cache goes and updates the database. Of course, there are a lot of issues that the cache must address. As soon as you say the cache has to update the database, what if the cache server crashes? What happens to that queue? So in case of NCache, the queue itself is replicated to multiple servers. If any server goes down, you don't lose the queue. And then there's also retries. What if that update fails? Then you can retry. You can also do batch update. So if there are a bunch of them, you can say do a bulk update. So it can optimize things further. So write-through and read-through are very, very powerful features. There's what I call server-side code. This is your code that lives on the cache cluster. It lives here. And keeping that code on the server simplifies your application. So the more code you push down, the simpler the application becomes. Any questions?
With the right behind, how do you deal with the concurrency stuff?
So the same way as you would deal from your application, you're just making a database call. The only issue is the commit and the rollback. From the write behind, whatever that one write-through was, that if it's updating multiple tables, it has to have the logic of commit and rollback within itself. Because one cached item could be mapped to multiple rows in multiple tables. In that case, you could, let's say it's an order object, and it has embedded inside it all of the order items. Why have it as a broken up? That's a classical argument that a NoSQL JSON database uses, right? Aggregation of data into logical. That's how you're seeing it in the application. So why break it up? So you cache that entire order as one item, and it contains a bunch of order items. Now, when you add the order to the database, it has to be a transaction of multiple tables. So the write-through will have the logic where it's going to update. It'll add a row in the order table, then it'll add a bunch of rows in the order item tables, and it'll say commit.
So every cache item that you use would have its own write behind and its own read behind it?
So there's a write behind that will be able to handle all sorts of cache items based on the key.
So you have one, and then you have like a state.
In case of NCache, you can have multiple write-through or read-through providers, and they're all named. So that's how you can isolate different groups of data, especially if you have multiple applications using the same caching infrastructure. But usually within one application, you'll have one write-through usually. which will then, the key is itself is the key. You know, the key tells you what the data is and where to go.
Okay, so the key, so you look at the key and then you have like a switch statement or whatever to go and
Exactly. So let's say here, for example, the write-thru source is actually, it's an operation. The operation contains the type of operation and also the value also. So the value now is your customer object, let's say. The customer object, you know now it's your code that it has to have a customer ID and all the other attributes. It needs to go do all of that.
You can set up the entities. That's how it goes about.
Exactly. So yeah, so the write-thru could be making an EF call. You know, it could be an EF client itself. Any questions about the benefits of read-thru, write-thru, about where you should use it and how do you, what do you gain by using it? Okay, now that, let's say, you're convinced that you should use caching, you have the different use cases where now you're confident of caching a lot of data. So now cache is starting to look like a database. You know, it's starting to have a lot of, you're going to have millions of items in the cache. So when you have millions of items in the cache, is it good to just read things based on a key? No. You know, if the only way to read items from the cache were based on a key, your application would be very, very challenging compared to if you could do things, well, give me all the things based on this search criteria. So searching and grouping becomes a very, very powerful need or very important need of a cache. Again, as I said, the purpose is for you to understand what are the benefits. The benefit is if you can cache more and more data. The more data you cache, the more you need to see or have more of the database type of features. One of those features is to be able to do metadata. In database, you can have indexes on a lot of different attributes. Here you can do tags, name tags, and actually when you cache the objects, in case of NCache, it also lets you create indices. So you can index an object, let's say a customer could be indexed on city attribute. Because you're going to search on city, so it should be indexed. If it's not indexed, that search is going to be really, really painful. Imagine millions of items that you have to first deserialize to inspect every object, just to know which customer is in Orlando. You know, not a good picture, not a pretty sight. So grouping, subgrouping tags and name tags, again, from a coding perspective, very simple. I'm just going to quickly show you this. From a coding perspective, very easy to use. You add a bunch of items and you assign it tags, and then you, I'm sorry, group and subgroup, group, subgroup, and then you say get group data, or you could also do an SQL search and say, give me all of the product object where the group name is electronics. So grouping and subgrouping tags, and tags are also something that App Fabric provided. By the way, App Fabric is being discontinued in February. We've got 10 more minutes, so I'm going to speed it up. Again, finding data is related to grouping data. You want to be able to search data based on SQL. So I think where's object query language? There it is. So I could basically, I've got a bunch of data and I could issue a SQL statement and I can specify multiple attributes and pass parameters and I'll get a record set back in case of NCache. And just like SQL Server, although it's a subset of the full SQL, you know, it doesn't do joins. Instead of doing join, you can do grouping and tagging, and that's how you can group multiple objects together. In this one, no, this is not being executed on SQL. This SQL is being executed within the cache. So the cache is the one that's indexing. Cache is the one that's searching its own cache.
Okay, so if you have some data that's in the cache, but other data that's in the database,
then don't do SQL. Well, the only time you want to do SQL is when whatever data set you're searching is all in the cache.
So the search, is it a wildcard or is it just an exact match? Or?
It can do wildcard also. In case of NCache, it can do, you can use the like operator on it. You can do range searches, you can do aggregation, a bunch of stuff. The only thing that you can't do are the joins and nested queries. So being able to search, and then the same thing goes with link. So so in case of link, NCache has implemented a link provider. So the iQueryable interface, you go and get that collection from NCache, and then you do a link query just like you do against any other object collection. And it's going to go ahead and get you a collection of these objects, the product objects back. So if link is your really comfort zone in terms of searching, use link to search. When you issue this query, you're going to the cluster. That same query is going to be sent to all the servers, and the results are going to come and get merged and then shown to you. So it might, although it looks very simple here, behind the scenes there's a lot of work being done by NCache. So we have SQL and link. We also have bulk, and as I said, you can do indexing. Runtime data sharing. I'm just going to very quickly. There's key-based events. There's cache-level events. There's pub/sub events. There's a continuous query. Continuous query is a feature that's like a SQL dependency feature, except it's on the cache. You're asking the cache to monitor a data set for you. So just like we were using SQL dependency and asking SQL Server to monitor this data set and said, if this data set changes, please notify me. Now you're asking NCache, saying, please, here's my SQL statement. Select customers where customer.city equals New York. And you're saying, if any customer that matches this criteria is added, updated, or deleted from the cache, please notify me. And that could be any place on the network, any place on the cache cluster, and you could be at any of the clients. You'll be notified. So by having those types of features, now you can suddenly monitor what's happening to the cache and be notified instead of polling things. And that's what I was saying. The cache becomes a really powerful runtime data sharing platform. Any questions on this? I'm not going to go into more detail on this because otherwise we won't have time left. We've got only 5-6 minutes. Okay, I'm going to skip this also. Any cache that you use has to have dynamic. It has to provide high availability, which in case of NCache, it's got a peer-to-peer architecture. We've talked about the topologies, where the replication must happen, but not at the cost of scalability. There's one feature that I do want you to know, which is called client cache. Some people call it near cache. This is actually a cache that sits locally on your application server box. It's like a standalone cache, except it's not standalone. So it can even be in proc. It can be within your application process. That means you're actually fetching things as on your object heap. Your heap has data in object form. Nothing beats that performance, right? If you can just get that data from the heap versus even going to a cache local box out proc. Because when you go across processes, it has to go through IPC, it has to do serialization, deserialization. When you go across the network, it's even more. When you go to the database, it's phenomenally expensive comparatively. So this is a local cache within your application process or locally on the box, but it stays synchronized. You don't do any special API programming for the client cache. You just make the calls to the cache. In case of NCache, it just plugs into the configuration change. And it intercepts the calls, and it keeps whatever you're fetching, it keeps a copy of it locally. So the next time you fetch it, it'll automatically get it from the local cache. Huge boost in performance. This is something that only NCache has on the .NET side. On the Java side, there are other products that have client cache. But on the .NET side, this is like a cache on top of a cache. And this is the reason many people, when they move from the standalone in-proc cache to a distributed cache, they complain. My performance has actually dropped. My application is slower. I thought distributed cache was supposed to increase my performance. And we tell them, no, it's supposed to increase your scalability. Nothing matches a local in-proc cache. Nobody can. I mean, this is not something that we can invent and do something. You're going across processes. That's a cost you have to take. So then we say, well, one way you can overcome that challenge is by using a client cache. So a client cache, again, is a subset. Usually you would have 16 to 32 gig in each cache server. So if you have 3 to 4 servers, you've got about 100 plus gig of cache data, potentially. And the client cache may be 1 gig, maybe 2 gig, maybe 3 or 4 gig maximum. And depends on how many worker processes you have. If you have only one worker process, make it 4 gig. If you have 8 worker processes, which many of our high-end customers have on their web tier, then you don't want to have 4 times 8 just as a client cache. So then maybe it's good to have a 4 gig out-of-process cache, which is still better than going to the caching tier. It's still faster. Or you could have a smaller 1 gig or less than 1 gig cache, which is in proc. Now you have 8 copies of it, but they're all synchronized. So definitely a client cache is something you must consider using if you're going to gain the value out of a cache. Now, my goal in this is not to sell you NCache's features, but to say what a good cache must have. And as I said, many of these features you will find on the Java side. Java is a much more mature market on the caching side. They use the word in-memory data grid instead of distributed cache. But whatever feature you're seeing with NCache, you'll see many of them also on the Java side. But on the .NET side, NCache is the only one. Another feature is, well, if you have multiple data centers, you'd want your database to be replicated. So why not the cache? What are you going to do? Are you going to rebuild the whole cache? What about the shopping cart? What about the sessions? So multiple data centers is a reality, and the cloud has made it even easier because there's no effort on your part. You just go and say region 1, region 2, and voila, you've got 2 data centers, right? And but the underlying problem doesn't go away, which is if you use a distributed cache that does not support WAN replication, you're stuck. You can't have an active, or even an active-passive multi-data center solution without the cache being replicated. So very important feature. And NCache, of course, has this. I've already given you the hands-on demo. NCache NCache is the oldest .NET cache in the market. We were launched in 2005, much older. So I'm going to quickly go over NCache versus Redis, very, very high level. And that's because Redis is a lot of people come and ask us, so how do you compare with Redis? Since Microsoft chose them for Azure. Redis is a great product. It's super fast. It comes mainly from the Linux side. It does not have a lot of features. It doesn't win on features. It just wins on the fact that it came from the Linux side. And Microsoft wanted to capture the AWS market. So they couldn't adopt a .NET solution. They had to adopt multi-platform. So their Linux version is very stable, very good. But the Windows port that Microsoft did itself is kind of an orphaned port. Microsoft doesn't use it themselves. When you go to Azure and use Redis, you're not using the Windows port of Redis. You're using the Linux version. So if you're not on Azure and you're going to use the Windows port of Redis, beware. Nobody owns it. Redis Labs, if you go to their website, they don't even have a Windows download. They only have Linux downloads, which is the creator of Redis. Microsoft, as I said, themselves, they didn't put their money where their mouth was in terms of the use, the commitment. So NCache is the only viable option for you, and it's open source. So if you don't have the money, go with the free open source version. If your project is important and you want support and more features, which is the enterprise features, the enterprise NCache is built on top of open source. It's not like a separate thing. Open source is not orphaned. We own it, we maintain it, and the enterprise is built on top. So open source has to be stable. But if you want support and more features, then just purchase the Enterprise Edition. We're native.NET. We developed in C#. We've got Windows Server 2012 R2 certification. We're going to get the next one also soon. So we're on top of the game as far as Microsoft is concerned. We're pretty much .NET. That's what we are. We have a Java client, but almost all of our Java usage is by customers who buy NCache for .NET, and since they have it in-house, they also use it from Java. So our bread and butter, our entire survival is on .NET. So we're always going to be on the latest and the greatest, the first and the easiest. So that's pretty much the end of my presentation. Any questions? Okay. Thank you very much, guys.